If you found your known displacement contains code number 3, 4, 5, 6, then the known force vector should contain the remaining code numbers. Okay? If you found some code number in the non-displacement vector, the remaining code number should appear on the other one, so that when you combine them together, they form the whole set of code numbers. They form the whole set of degrees of freedom. We mentioned right here, right, in this matrix equation, if you know one side, then the other side is unknown, or in reverse manner. It's helpful to check your formulations. Now you can put QK, DK, DU, QU into our full displacement relationship. The structure stimulus matrix obtained from example 1. The Q and D vector, I just put them according to the code number order. No special things. K is evaluated already in example 1. So how to solve the problems? First thing you can do a matrix partitioning, cut the matrix into 4 parts. K1, the dimension of K1 should be consistent to the unknown displacement vector. The unknown displacement contains 2 elements, or mathematically, PU is a 2x1 vector. In this case, K1 should be a 2x2 matrix. The size of K1 depends on the size of PU. You can understand easily because, according to our previous discussion, QK equal to K1 times DU, right, plus something. When you do matrix multiplication, their dimensions should be consistent. 2x2 matrix can be multiplied to another 2x1 vector. The dimensions should be consistent. Otherwise, you cannot complete the multiplications. That's why the size of Q1 depends on the size of PU. Q1 is a 2x2 matrix in this case, in this example. I extract them out. QK equal to Q1 times DU. By solving this equation, you can find out the unknown displacements D1 and D2. When you go back to the previous theoretical part, there should be something behind, right? K12 times dk. K12 is here. K12 in dk. But you can see that dk is a 0 vector. 0 vector times K12 gives you 0. So the outcome is that it seems that K12 is useless. It's redundant, right? If you don't know K12, you can still able to solve for unknown displacement. This explains why when we construct this first matrix, I mentioned that some are useless. This is the reason. Because that part is multiplied to a 0 vector. It gives us 0. K12 is totally useless in the calculation. Then you can think in the other way. When you solve this problem at the beginning, you have to do a long calculation to assemble the matrix, right? So normally, I suggest students, before doing this matrix assembly, I suggest students to have a look of the overall picture first, to see which part is useful, which part is useless. Try to put more time on the useful parts. For this useless part, say for example, Q12, actually, you don't need this part, right? Without this part, you can also able to solve for D1, D2. We solve for unknown displacement first according to Zipf's method. Unknown displacement to you. Solve this equation. How to solve it? There are many ways to solve for this matrix equation. You can use our high school method, convert this to two equations. First equation, second equation, convert this to two simultaneous equations. And then two equations, two unknowns. You can use like method of substitution to find out the answer. Or you can use matrix method to solve this problem. How? Find out Q1 inverse. Find out Q1 inverse. And the more method. You can use Gaussian elimination. Gaussian eliminations. So there's more than one way to solve for this kind of matrix problem. Depends on which one you most familiar with. Right here, I just change this as two equations, equation 1, equation 2, and then use substitution to solve the problems. The first equation will be something like this: 0 this row and this column, right? EA 0.405 D1 plus 0.096 D2. First equation. Second equation, minus 2 equal to EA 0.096 D1 plus 0.0128 D2. Matrix multiplications, you can convert them back to two simultaneous equations. Two equations, two unknowns. Suppose we can find out the outcomes. Simple math problems. D1, 4.505 over EA. D2, minus 19 something. This is how you can find out unknown displacement. D1, D1, D2, or simply Du. Using matrix method. If you know unknown displacement, you can use it to find out the unknown actions if necessary. How to find out unknown reactions? Say, for example, Q3. If you want to find out Q3, the calculation is quite straightforward right here. Simple matrix multiplications. This row times our displacement vector give you Q3. When you find out unknown reactions, there's no need to do any matrix inverse. Just a simple multiplication using the displacement that we just calculated. Or you can operate as a whole using matrix. Unknown displacement, unknown reactions equal to K21 times du. This part, K21 times du plus K22 times dk, but again, 0. Again, you can see that this part, K22, is redundant in our calculation. K12, K22 is useless in our problem, example 3. Only the first two columns are useful. Among the whole big spectral matrix, we have 36 elements, but only the first two rows and first two columns are helpful. By doing this matrix multiplication, K1 times our displacement gives us the reactions. Q3 is negative 1.5. Negative 1.5 means it's pointing opposite. I change the color a little bit. Q3, 1.5. Negative means opposite to the direction of 3. That means it's pointing to the left hand side. Q4, 0. Q5, 5 is here, positive, 1.5. Q6, upward, 2. Our applied loading is acting at node 2 here. So it satisfies force equilibrium, horizontal equilibrium, and moment equilibrium. It should satisfy equilibrium because we're playing with static problems. For static problem, it should satisfy equilibrium. Summation force equal to 0, or summation moment equal to 0. Okay. There's one one point here. This one shows you some idea how to check your answer. What I mean is that, well, in the previous page, we evaluate our unknown displacement. D1, D2. D1 is positive, D2 is negative. What is the meaning of positive D1, negative D2? Maybe I used this page here. We have code number on this page. The structure is now under downward force at node 2. Then what is our expected diffraction of these structures? We expect the structure will move downward because we undergo downward force. And it will move a little bit to the right-hand side. It seems that the expected diffraction should be something like this, when this truss is under downward force. That means D2 should be negative, D1 should be positive. This is my first impression from the picture. And then I should think that D2 should be bigger than D1 in terms of the magnitude, because direction 2 is along the loading, so the value should be bigger. You can use your inspection to double check your answer to see whether your answer is correct in terms of direction or in terms of the relative magnitude. D1 is bigger, D1 is negative, D2 is bigger, D2 is negative. Right? It seems it's consistent with our inspection. This is what I mean in this statement. After doing your calculation, you can double check with your structural sense to see if your calculation, if your value is correct or not. You know, when you conduct this kind of complicated matrix calculation, it's quite easy to make some problem errors in the calculations. So the support reactions are shown graphically on this page. Depends on what information you need. Here I show you how to calculate displacement, how to calculate reactions. You know all the numbers. And I also show you how to calculate the member actual force. In this example, I show you how to calculate member actual force. Member actual force. We have two members, member 1, member 2. And member 1 is a horizontal member, lambda x is 1, lambda y is 0. Member 1 is here. You can use the equation on the top right-hand corner to evaluate the member actual force for member 1 and member 2. We know lambda for member 1, we know the length, we know the displacement as well. For element 1, we know displacement 1, 2, 3, 4. We just evaluate before. After doing the previous answer to these equations, then you have the numbers. And same for element 2. Just a simple substitutions. This is one way to find out the member actual force. Or you can use our previous knowledge. Once you know the reactions, you can use joint equilibrium, or you can use method of section to find out the member actual force. There's always more than one way to solve the problems. I showed you how to use matrix method in the notes. But in the past, we have learned different theories. They are also correct. That is what I want to mention. You can use equilibrium, joint equilibrium, method of sections, Or if you like, you can use this matrix method to find out the actual force. Negative for number 1, positive for number 2. Negative mean compressions, positive mean tension. Okay, this is example 3. Let us stop here for today. I just present up to example 3. And what next, I would like to jump to the tutorial sections. Because in tutorial sections, I would like to solve one common questions about how to assign code number, how to assign member orientation. These are some common questions that I received almost every year. So I think it's good to have a tutorial part first. Example 4, I will discuss next time. But before moving on to our tutorial sections, maybe I give you a short break. I delay a little bit, maybe I give a recognition break of 3 minutes. Cái mà để cái số cái ngoại ngoại thì nó là ai được ra học những người tiếng Anh cái ngoại học của đây là cơ bản has okay. Let us move on to the last part for the today class. The last part is a short tutorial section to let you know more about how to do the analysis using trust, using Sylles method. How to apply that method to trust structures. In these sections, we would like to show you how to use this method, trust structures, and then we will study what happens if we change the orientations and what happens if we change the code number diagram, code number arrangement. These are two common problems I received almost every year. Let's have a look at this example. I do this as usual. We demonstrate the procedures again. And that means that you can see version 2. You will see version 2 and version 3. At the time, I'll make some changes of setting. Right here, let us treat it's a normal question. Suppose we have two trust structures with two members. In this question, you're asked to do two things. First, find out displacement at node A. Second, find out the member action force along the member 1 and member 2. We have some material properties and cross-sectional properties. The elastic modulus is 200 GPa. The cross-sectional area for member AB is 6,000, member AC 8,000. This time EA are not simple, they are numerical values. You know the length of the member, you know the geometry of the structures. Using the geometry, you can calculate the length of each member. So this one is quite classical. At the beginning, what we do, step 1 is discretizations. We need to arrange our code number diagrams. We need to arrange the number orientations. Following, arrange the number orientation from left to right. From left to right. That's why we have the orientation in this arrangement from left to right. Number 2, we cannot point upward. If you point upward, then the horizontal direction becomes pointing to the left-hand side. I'll show you what happens if we change the number orientation later. In example 1, version 1, let us follow this number orientation. Number 1, point from point B to point A. Number 2, pointing towards point C. In the next example, I will change the orientation to see what happens. We have two members, 3 nodes, node A, node B, node C. Each node consists of 2 degrees of freedom. So in total, we have 6 degrees of freedom. The code number up to 6. Where should we put number 1? Suppose we follow the textbook suggestions. We assign code numbers starting from positions with unknown displacement first. Copy Tn. Tn, we have no displacement. No, zero displacement is a known value. Right? On C, another piece of code, 0, 0, known values. On A, 3n, unknown, question marks. So if you follow the textbook method, you can assign code numbers starting from point A. We normally start from horizontal and then vertical, X and Y, right? Normally. Unknown displacement appeared along code number 1, 2. They show right here. 1, 2. We use small number to denote unknown displacement. In the formulation, you will see the advantages of doing so very soon. Why we use small number for unknown displacement? Then what about the other? The other 3, 4, 5, 6. You can assign arbitrarily. 3, 4, 5, 6. I arrange right here. 3, 4, and then 5, 6. They describe the position of unknown reactions. So we complete our code number diagram. Based on this diagram, we can jump to the next step. Next step is to evaluate K1 and K2. You may need to know the coordinate first for point B, point A, and point C. To find out the coordinate, you can set your global coordinate system at the bottom left-hand corner. Then point B coordinate is 0, 0. Point A coordinate is 6 and 4. Point C, the coordinate is 9 and 0. If you know the coordinate, you can evaluate the direction cosine. Lambda is lambda y immediately. Xn minus xn. We use the coordinate at not f minus the coordinate at not n to calculate lambda x and lambda y. F minus n, quite easy to remember. How to define not n and not f? Depends on the member orientation. The arrows point to not f. The other side should be not n. Same for element 2, f and then n. So once you set up the number diagram, member orientation, you basically know all the symbols. You can mark them down on your picture, on your answer book if you like. In step 1, actually, you can also put down the known displacement, known force vector. We call it dk and qk. dk, or 0. Consists of degrees of freedom, 3, 4, 5, 6. qk, 1, 2. 500 for q1, because this structure is undergo horizontal force along horizontal direction. The horizontal direction is number 1. So q1 is 500, q2 is 0. Q3, Q4, Q5, Q6, they are reactions, unknown. Unknown reactions we group it into QU, right, according to the previous symbol. And then you can put down displacement. Displacement, D3, D4, D5, D6, describe what happened at the support. They are all 0. dk, 4 numbers. You can also double check the code number. For the known displacement, you can find out degrees of freedom 3, 4, 5, 6. The remaining 2 numbers should be appeared in qk, known force vector, so that they can complete the whole series of the code number. So it seems that our given information are all right. Then we can proceed to the next part. The next step. Find out K1 and K2. I will show you what happened if we change the member orientation and change the code number later. Firstly, find out the member sequence matrix using the same equations. And you don't need to memorize this matrix, because normally I allow students to bring formula sheet to the examination venue or to the quiz during the quiz. So you don't need to memorize these kind of things, but you need to know how to use it. So, for example, you need to know how to calculate lambda, and you need to know how to arrange the code number and x and y. So I extract element 1 on this page. Let's make the presentation more clear. And this is the member orientation pointing towards point A. This member orientation affects the positions of N and F. The arrow always points to node F. The arrow is pointing towards the node F, far node, while the other side should be node N. So in this case, you know the arrangement Nx, Ny, Fx, Fy immediately. 3, 4, 1, 2. What happened inside the matrix? Lambda x squared, lambda y squared, lambda x, lambda y. To evaluate the matrix, you need to know these 3 patterns. So in the following part, I calculate them separately. The length, L1, you have the 2 coordinates. You can use this formula to find out L1. 7.21 meters. Lambda x. I put the formula here. We use the coordinate at not F minus the coordinate f of n, f minus n, and then over the length. Lambda x from 83, lambda 1 from 55. You can calculate lambda x squared, lambda y squared, lambda x, lambda y to speed up your calculation because we have only these three patterns inside the matrix. Once you know the number, put them at the four positions. You can also calculate U over here, which is a constant series. We call number 3, 4, 1, 2. Nx is 3, ny is 4, and then fx and fy 1, 2. Put all the things together becomes our first element sequence matrix. The order is 3, 4, 1, 2. Nx, ny, and then fx and fy. The first element, for example, the first element is equal to EA over L lambda x squared. We know all the numbers. We know E over L, we know lambda x squared. The value is approximately equal to 115,207. You just repeat this several times. Then you have the whole matrix. Some remarks at the bottom. We have only three patterns, and then the matrix. Symmetrical. You don't need to evaluate the whole one. You just need to evaluate one triangle, and then reflect to the other side. This is the excess of symmetrical. Which may somehow help you to speed up your calculations. You can verify the answer using your calculator later. Quite a various mathematical procedures. For element 2, you just actually follow the same procedures. Define the coordinate, define the number orientation, define node n and node f, then you can calculate lambda f and lambda y in this case. The method is now oriented towards point C, according to our given definitions. So here is node f. Node f is the bottom node. Node n is the upper node. If you know where is node n and node f, then you know nx and y. You know fx and y. Fx is here. 1, 2, and then 5, 6. You know the arrangement of element 2. Then the values depends on lambda x, lambda y again. This element, the length, you have to calculate again. The length is not identical to element 1. The length is not identical to element 1. You have to calculate the length again. And then use the coordinate to find out lambda x and lambda y. Remember that we use the coordinate at node f minus the coordinate at node n over L. F is the bottom node, n is the upper node. So 9 minus 6 over 5 equal to 0.6. And then lambda y. Lambda y is equal to yn minus yn over L. Yf is 0. Yx and yn is 4. 0 minus 4, which gives us a negative value. 0 minus 4. Be careful about the positions. And then E over L, as usual. Then do simple calculations. Lambda x squared times E over L. Lambda y squared times E over L. lambda A is lambda Y times E over R. Just do the figures again. But we have different parameters. Again, you can utilize the symmetrical properties to speed up your calculations. This is one way how you can speed up your calculation using symmetrical arrangement. And then you have only three patterns, right? You have only three patterns according to our discussion here. Although there are 16 terms, but only three patterns appear. Some positive, some negative. If you have more elements, then you need to go for all elements. In these questions, we have only three measures. So we finished step 2. Step 3 is to evaluate the Banker series measures. Now we know all the measures. Part 3, assembly. Add up all the element matrices together to form the whole structure series matrix. In the solution right here, you can see that I firstly enlarge element 1, element 2 to a 6x6 matrix with the size identical to our structure series matrix, the K. The K is a 6x6 matrix, right? Because we have 6 degrees of freedom in these structures. And firstly, enlarge K1, K2 to 6x6 matrix, and then sort the element in ascending order. Code number start from 1 to 6. For K2, I do the same thing. K1 only consists of code number 1, 2, 3, 4. K2 contains the code number 1, 2, 5, 6. That's why there are some empty. Empty means 0. 0, 0, 0. Fill them with 0 column, 0 row. They have two identical signs, and you can see that it's quite easy to observe which part should be overlapped with each other, which part have isolated. Combine these two measures, and then up together, position by position. These enlarged measures just help you to visualize which parts should be added up with each other, but not compulsory. When you add up all the elements together, then you can form this whole 6x6 matrix with totally 46 elements. Again, you can utilize symmetrical property. You can utilize symmetrical property. No need to evaluate all 46 groups. Just need to do one half. And then use the mirror image to find out the other half. This is the first shortcut, symmetrical property. The second shortcut, I think, is more useful. Before doing this addition, I encourage students to have a look at the overall force displacement relationship. Before knowing K, I suggest students may have a look about the overall force displacement relationship. You can actually do it at the beginning in step 1. In step 1, after defining our member orientation, our code number, we have no idea about what happened at the middle. Okay, at the beginning, we know QK, we know DU, we know DK, we know the arrangement of QU, right? So at the beginning, step 1, you can set up the prelim equation of the force displacement relationship, Q equal to KD. Although you don't know what it looks like for the series matrix, but from this expression, because you know the number of unknown displacement, right? Which means you know the dimension of Q1, you know the dimension of Q2, Q21, and Q2. From these expressions, which part are useful to evaluate displacement, evaluate reactions? Q12 always multiply with dk, right? But dk is 0. So it seems that Q12 useless because it's worked with a 0 displacement vector. K22, similarly, K22 multiplied by dk. also give you 0. So at the beginning, you can see that column 3, column 4, column 5, column 6 are useless. They will not help you to do anything because they always work with 0. So you can ask yourself, hey, why I need to know column 3, column 4, column 5, column 6? Actually, they will help you to solve the problems, right? That's why I suggest students firstly take a look at the overall for displacement relationship, and then to see which part are useful. Only need to evaluate the part which are helpful for you to solve the problems. Then what about the useless part? The useless part, normally I allow students to write the things symbolically. So for this part, you can express them using K12. Here you can express them using K22 or the other symbol as you like. You can express them symbolically. You don't need to evaluate the exact number or K12 and K22 because they won't help you to do the problems. Only need to evaluate the numbers along the first 2 columns. But for the example here, I do all the calculations so that you can practice how to do the matrix assembly. But in reality, just need to evaluate the useful parts. Anyway, after some discussions, let's continue to the next part. Step 1, discretization. Step 2, element matrix calculation. Step 3, matrix assembly. Now, step 4, solve the force displacement relationship. Firstly, I construct the force displacement relationship Q equal to KD plus 1 additional factor. I will discuss what it is later. It's something related to the next sections in the notes. But it's 0. It is 0 in these questions. So actually, you can ignore the Q0. Q equal to KD. Q composed of QK, QU, D composed of DU, DK, and so on. Right. Then you have these matrix equations. You are matrix partitioning. You can see clearly which part is useful from these equations. Q1, very helpful for you to solve unknown displacement. So make sure that you get the correct numbers within K1. K12, actually you can skip it. You know du, dk, you know the arrangement. Again, I just remind you that not all the elements are useful. You can symbolically express the useless parts. For Stevens method, we are going to solve for displacement first. That's why we call this Stevens method at the beginning. To solve displacement, we use the first part of the equation, the top row 1, equation 1. Equation 1, Qk equal to K1 du plus K12 dk, but dk is 0. So only the first term in the equation, Qk equal to K1 times du. You can use your own way to solve this equation. Okay? There are more than one way to solve this equation. You are not necessary to follow what I put down here. You can use your own method. You can solve for 2 simultaneous equations. You can use matrix inverse, or you can use Gaussian accumulation. Up to you. Okay. I'm not really care what you use as long as you can find out the answer. I show you 2 methods in the solution. Method 1, I use matrix approach. I try to find out the inverse of K1. Because you can see that if you multiply the inverse of K1 on both sides of the equation, then the right-hand side becomes only du. The left-hand side equal to K1 inverse times Qk. This multiplication gives you unknown displacement du immediately. So simply speaking, if you know how to inverse the matrix K1, if you know how to inverse this matrix, then the problem solved. how to inverse a matrix. If you forget, you can go to our matrix analysis notes and upload that in Moodle. You can download from Moodle. This is the matrix inverse. I put a view stack on the top right-hand corner. If you want to find out the inverse of matrix, you need to firstly evaluate the determinants of the matrix, of the matrix given one. And then you can construct the inverse matrix using 1 over the determinant times a so-called contractile matrix. And then by doing the calculations here, you can get the inverse matrix. But if you have the inverse matrix times QK is the non-force factor, then you have the displacement. I just made it right here. Matrix inverse. But for this kind of simple problems, I think you can solve two types of simultaneous equation directly. I think it is more efficient in this for this simple scenario. Two equations. Two unknowns. You can solve it easily using substitution or elimination or the other else. You can also get the same answer. I changed the unit a little bit. I convert to millimeters because we don't want to use mm for displacements. But if you change that back to meters, they are the same. So the method of analysis will not affect the answer. You can always get the same one. So you can decide which method is more appropriate to you, which is inverse or solving simultaneous equations. For your information, for the quiz or final examination, because of the time constraint, normally I will not give you too complex questions. Normally I give you in the quiz and examination, I normally give you a known displacement up to three unknown displacements. I think that's sufficient for the difficulty in the quiz and examination. Which means that if you want to use matrix inverse, you need to know how to inverse a 3x3 matrix at most. Okay, 3 unknown displacement is something that you may need to handle in the quiz or examinations. At most 3, which means that it can be 2. It depends on the difficulties. But for assignment, I may give you more unknown displacement because you can use like Excel to find out to solve the problems. I will let you know how to do it in the next topics. If you go to the the mathematics textbook, I believe that they show you even more methods, not only these two. And from this picture, D1, moving horizontally, D2, upward. The structures now undergo a horizontal force, 500 at the top of the structures. And then our final outcome is that it's moved horizontally and vertically. The horizontal movement is bigger, 2.41 millimeters. It seems like it's not satisfying, consistent to the applied force. Okay, in this direction, appropriate. You can also use Gaussian elimination or the other methods to solve the problems up to you. Finally, you are asked to find out the member actual force. We have two members. Again, you can, in this question, because I did not ask you to find out reactions, we have no reactions. So I use this equation to find out the member actual force. If you have I did not ask you to find out reactions, right? I just asked you to find out displacement and member actual force. So do not do extra things in the quiz examination. I did not ask you to find out reactions. That means we don't need to show you the calculations. And we use this equation to calculate the actual force. Member AB at this point. For member AB, I remember that in step 2, when we construct our element sequence matrix, we have lambda x, we have lambda y. I just copy the values right here. You have these two values already when you calculate the element sequence matrix. Element 1, element AB, we have a 4-nodal displacement. The element is pointing towards this direction. Right? This is the main orientations. So the node on the left is in, the node on the left is on the right is F, node N and node F. The displacement at the node N is called dNx and dNy. The horizontal displacement at node N is called dNx. dNy is the displacement at node N along the right directions, dNy, and so on, dNx, dNy. What about the displacement? Up to here, we just solve for the unknown displacement. Some are 0, some we just solve. So actually, we know the nodal displacement for these two truss members. Say, for example, node N. Node N is our support, pin support. So D3, D4 are 0. Node F. Node F actually is the top node of the structures. We just count out the displacements at this node. So you can see that there is no unknown in this equation. Everything are well defined. EA over L, we know it. Lambda A is lambda Y. And then D3, D4 are 0, support. D1, D2, the displacement, we just calculate before. Then we have the actual force, QAB. 400.6. Positive. Positive mean is intention. Positive mean is intentions. After doing the calculations, you may have a look at the problems. The structure is under horizontal force. So it seems that member AB should be intention. Right? The force is going to pull the structures horizontally. So it seems that QAB should be positive. And this, our direction is correct, positive. The values depends on your calculations. Okay, the values you have to check in the precise manner using calculations. But this direction, correct. Do the same thing for element AC. For element AC, you have different number, you have different length. For member AC, member AC is member 2. Member 2 is pointing towards the bottom node. When you take a look on the structures, member 2 is pointing towards the bottom node. So the bottom node is node F. The upper node is node N. Depends on your orientations. The arrow points to node F. The other side is node N. It helps you to define how to set up the displacement. dNx, dNy, dFx, and dFy. This time node F is appeared at top, node F is bottom. So Nx, dNy, dFx, dFy. F is coincide with the support. So the D5, D6 are 0 at the support. Negative. The value is negative in total, minus 200 something. Again, it makes sense because of the force, the applied force is moving to the right hand side. So it seems that number 2 should be in compressions. One tension, one compressions. If you want to check the answer, you may also conduct a joint equilibrium at node A. You can conduct a joint equilibrium at node A to check the values of the actual force. Joint equilibrium. But this is the traditional procedures, how you use this method for truss analysis. But as I mentioned before, I would like to show you the other examples. Say, for example, what happens if we change the member orientation? In this one, in version 2, we consider the same problem. I would like to let you know what happens if we change the member orientation. This time, we reverse the member orientation, but we keep the code number arrangements to see what will happen in our formulations. I will not go through the whole calculation because actually they are the same. And we'll let you know which part are different. Well, at the beginning, we also put down the known force, known displacement, based on the given code number diagrams. We keep the code number diagram, so there's nothing changed right here. Then we'll start to change if you reverse the member orientations. What happens if we reverse the member orientation? You will start to see some difference when you calculate the element sequence matrix. Why? When you calculate the element sequence matrix, you need to define where is not N, where is not F. And F. Since you reverse the member orientation right here, the arrow is now pointing to the bottom node. So the bottom node becomes not N. The upper node becomes not N. N, F, reverse. Compare with the previous version. What happens if you reverse N, F? When you calculate direction cosine, number A, number Y, we use the F coordinate minus the N coordinate. Okay. So if we reverse the definition of NF, you can see that lambda becomes negative. The sign of lambda reverse. If we change the member orientation, this is the first impact you can see. Lambda change, become monosized. You can again compare with version 1 to see the difference. But is it affect our calculations? Now the sign of lambda's change. But it seems that it will not affect our calculation. Why? Because when you want to calculate the structure and when you want to calculate the elements sequence matrix, you have to take the square or multiply both lambdas together. So this operation, square, cancel the sign, become back to normal. Right? So you can see that when you change the sign, it will affect a little bit at the middle, but it seems that it will not affect the values inside of the matrix. Right? The values also the same because we're taking square. But it will affect how we arrange the code number arrangement. Because when you use this element matrix, we start from nx, ny, and then fx and fy. We start from n to y. Now you change the arrangement, you change the order, which means that now nx becomes 1, ny becomes 2. So the code number becomes 1, 2, 3, 4, different from version 1. Different from version 1. Again, will it affect our calculations? The answer is no. Because when you want to add up K1, K2, K3, or element matrices together, you have to sort the matrix to ascending order. Right? This sorting will cancel out these changes. So I can tell you that if you change the number orientation, it will not affect your answer. Okay? Just keep your definitions consistent throughout your whole calculation. You will get the same matrix. Code number arrangement change, but not affect the final outcome because we have to rearrange the order when you do the matrix additions, assemble. Same for element 2. If you reverse the member orientation, then you have different sign for lambda x, lambda y. But when you calculate the matrix, you take square, so no effect. You have the same structure sequence matrix, no change. you can compare with version 1. We have the same structure as the matrix. Actually, I just copied from the answer from version 1, no change. Same K give you the same answer because we're under the samples. Same as version 1. So maybe orientation will not affect too much about your calculation. It affects numbers though. It will not affect the matrix itself. Matrix will remain the same. So don't need to so worry about the orientation. Just fix the direction at the beginning, okay, based on your own preference. Same as our solutions to tutorial 1, the previous examples, version 1. Version 3, the last version, last thing I want to show you. Version 3, we consider the same problems. This time we would like to keep the member orientation. The member orientation is identical to version 1, the first version. But you can see that I try to modify our code number order. This time I don't want to follow the textbook method. I assign code number from left to right. So we have 1, 2 here, 3, 4, and then 5, 6. I assign code number from left to right. I did not follow the textbook suggestions. So what would happen if I violate the textbook suggestions, assign code number based on my own preference? I would like to let you know in this example again in version 3. It's hard to see some difference right now. D1, D2, D5, D6, they are coincide and the pin support. So this time, the non-displacement appeared in code number 1, 2, 5, 6. Last time, 3, 4, 5, 6, if you remember. But here, 1, 2, 5, 6. 1, 2, 5, 6. The force, non-force, appeared with code number 3 and 4. If we change the code number order, then we have to write down the non-force, non-displacement vector carefully. They may be located at any code numbers. But all numbers should be appeared when you combine them together. If you see 1, 2, 5, 6 in displacement, then the force should contain the remaining 2 digits. About element calculations, because we keep the member orientation the same as version 1, so we have the same number as version 1, positive, positive, same values inside the matrix. But because we change the member orientation, right? Sorry, we change the code number order. We change the code number order. So we expect that the code number for element 1 will be different. Depends on your choice. This time, not n is at the bottom, and x is 1, 1, 2, 3, 4. Personally, I like this arrangement because the code number is automatically in ascending order, 1, 2, 3, 4. I don't need to do any sorting. It's already in ascending order. Save me some time. Element 2. Not n is here, and x 3, 3, 4, 5, 6. Again, if I arrange in this manner, the code number is also arranged automatically in ascending order, 3, 4, 5, 6. I don't need to do too much sorting for this case. It is quite helpful when you do these combinations, combining the matrix together. Because only one corner, this middle part, overlap with each other. You just add up these four numbers. The remaining part you can directly copy from K1 and K2. I think this arrangement of code number can speed up the calculation right here for matrix assembly. No need to do the sorting again. But what happens when you are asked to solve the problems, solve for unknown displacement? you start to see a big difference. And you know the reason is right. Haskell suggests you to assign code number from unknown displacement first. Right here, you can see that unknown displacement appeared at the middle. D3, D4 are our unknown displacement, not D1 and D2 anymore. Right? 1, 2 are at the support in our code number in this version. So where is schema 1? Where is schema 1 in this plot? This is the plot when you assign code number in arbitrary manner. If you follow the textbook method, just like the previous version 2, if you follow the textbook method, start to assign small code number at unknown displacement, and the outcome is that unknown displacement always appear at the top few rows. If you assign code number like me in arbitrary manner, right here in version 3, then unknown displacement probably occur at the middle or even at the bottom. This time is not easy to directly observe where is schema 1, 2, and 2, and so on. But don't worry, code number will not affect the answer. And how we can deal with this problem? The trick is quite simple. Just consider the row with unknown displacement. Consider row 3 and row 4. Okay, consider the row with unknown displacement. You can extract this row out using matrix multiplications. Say, for example, row 3. How to extract row 3 out? This row times this column. Then it becomes equation 3. Matrix is nothing. Matrix is just a collection of different equations. We put all the things together. Equation 3, equation 4, and then two equations. And the minus number times 0, and then 76,000 times 0, and so on. You can see that the first two columns always multiply with 0. The last two columns multiply with 0. Only the middle columns multiply with D3, D4. Give you some useful meanings. So the trick is that if you find that the unknown displacement appeared at the middle, don't worry, just extract the row that with unknown displacement. In this example, extract row 3, extract row 4 using matrix multiplications. This row times our displacement vector, and then the fourth row times displacement vector. Then you can get two equations, two unknowns. Then you can solve the problems. Just consider the rows with unknown displacements. The first two columns are useless because they multiply with 0. Same for column 5 and column 6. If you do this cancellation, it helps you to obtain schema 1. Schema 1 is not at the middle. Schema 1 is not at the middle. Schema 1 is now hidden inside the matrix, not at the top left-hand corner. But anyway, you can always solve the problems using the classical math approach. Two equations, two unknowns, you can solve for the unknown displacement. Although this time we call this D3 and D4, but they have the same numbers. Same as version 1 and version 2. So my conclusion is that code number orientations, they will not affect the answer. Just keep your definition consistent from the whole calculations. If you follow the textbook method, the advantage is that if you follow the textbook method, you can see unknown displacement appear on the top few rows. This is version 2. Okay? If you follow the textbook method, if you assign code number in arbitrary manner, like version 3, you can still solve the problems, but you have to pick the correct elements carefully. sometimes they appear at the middle, not at the top right hand, not at the top left hand corner. But once you identify the correct elements, then you can get the same numbers. Okay. This is what I want to mention today. Thank you for joining this class. Anyway, if you have questions, you may ask me right now. Otherwise, this becomes the end of this class. Thank you everyone to join this session, class 2. We will have another class on the coming Friday morning. How many do we